I'm Clifton McFate. I'm a researcher at Elemental Cognition. And as we discussed, I'm going to be talking about structural alignment as an abductive integer linear programming problem. So first off, structural alignment, analogy. It plays an important role in many cognitive processes, and computational models of analogy and structural alignment have had interdisciplinary value. If you want to hear more about that, there are several papers I can point you to that go through the many contributions of analogical models. What I'm talking about when I say analogy and structural alignment is the alignment of structured representations subject to a set of constraints. So as an example of an analogy or structural alignment, here at the bottom of the screen, I have a base case where my dog Pixie, that's the one on the left, the little spaniel there, is happy to see me. And on the right, a dog, Jackie O, who is my sister-in-law Mary's dog, is happy to see her. We can align these two dogs, even though they have some differences. Jackie O is a greyhound mix, has very different ears, for example, different coloring. We can align them based on their participation in higher order structure, namely that they're both happy to see their owner. With analogy, one of the most useful parts is that you can apply structure across analogies. So if I did not know why Jackie O was happy, I might be able to guess that it is seeing her owner that is making her so. And cognitive models of analogy typically, I would say typically treat an analogical reasoning this way. And historically, though, there's been debate over what constraints exist, how strong they are, and how they interact with other cognitive processes. And I'm going to be discussing two models today, SME and ACME, that make different claims about these theoretical assumptions. So SME is the structure mapping engine, and that is based on Gentner's structure mapping theory. And ACME is a different approach to analogy. They are both similar in that they are these kind of local to global matches trying to create a global satisfied alignment. However, they take different approaches. SME is symbolic. The constraints of structure mapping theory restrict both initial local matches and guide a greedy search for a global alignment. Whereas in ACME, constraints are edges in a network that excite or inhibit local matches. And all matches between same arity concepts are permitted to start with. So there's a difference between the kinds of constraints. In SME, identicality means that predicates have to be identical to match unless they are supported by a higher order structure. And that constrains the initial match space. One-to-one mapping means that one thing in the base can only map to one thing in the target. And parallel connectivity means that if an expression matches, its children also have to match. There's also a somewhat soft constraint called systematicity, which is a preference for mappings that share higher ordered structure. So going back to here, if Jackie O, if there were another greyhound or another spaniel dog in the mix on the right-hand side, I might still prefer the alignment to Jackie O because she's participating in the shared structure of being happy at seeing her owner. In ACME, the only real hard constraint is this identical arity. And then isomorphism, which is one-to-one mapping and parallel connectivity, is enforced as a soft constraint. So it's this excitatory or inhibitory alignment edge. They also use similarity, which is a function of how similar predicates are. And perhaps most interestingly, they allow pragmatic constraints and goals to influence the mapping. So you can say, for instance, I really want to align myself to the hero of the story, and that's going to influence the mapping process itself, which is an interesting feature. And there's some debate over whether that's actually a good or a bad thing. Another thing that's interesting is that SME is able to project inferences from shared structure, whereas ACME is not. It produces inferences from explicit goals. And what would be nice is a common framework that allows hard structural constraints like SME, but also soft biases. And part of the reason for that is to test these kind of hypotheses, but also to examine how outside constraints like cognitive biases might show up and affect the results of a match. And to that end, I'm going to be presenting the constrained abductive mapping model of analogy, or CAMA. And what I have done is I've formulated analogy, structural alignment, as a weighted abductive inference problem, where the goal is to explain two sets of observations, a base and a target, by their alignment to each other. So I can justify two sets of propositions based on how well they align. And following work by Inu and Inui, I am representing this as a 0-1 integer linear programming problem, which allows us to easily define hard and soft numerical constraints on the solve and make use of existing ILP technology. I'm also going to be generating inferences like structure map, like SME, and I'm going to be doing that as a way of explaining alignable but unmapped structures. And they can be assumed at a cost. And I'll get into all of that. Before I do so, some of the comments that I got on the response from reviewers was about, do we need another model of analogy? Is it, what are the contradictory claims compared to SME? Is this kind of a replacement for SME? No, comma is more maybe thought of as I think better expressed as an emulator maybe, rather than a model. It's not a process level cognitive model. I'm not claiming that people are doing ILP in their heads. I don't think there's evidence for that. What I think this lets us do is design different constraints and see what mappings look like under them, which is a good way for generating hypotheses and validating our thinking, I think. So to begin with, weighted abduction is inference to best explanation. I'm not going to spend a lot of time on this. I think most folks in this community are pretty familiar. But the idea is that you have an observation, for example, that I-95 is unsafe, and some axioms that can lead to that. And you want to make the lowest cost assumption that can generate that, that can explain that observation. So here, snow can make a road both wet and obscured. And so the cheapest assumption we can make is that snow is causing both of those things, which is causing the road to be unsafe. So this is the kind of classic weighted abduction. This is based on Hobbes's formalism. And what Ino and Inui did in 2011 is assign integer values, turn this into an ILP problem. And so what they're going to do is turn it specifically into a Boolean or a 0-1 ILP problem by assigning 1 if a hypothesis or a match or something is a part of the solution, and also keep track whether the hypothesis cost is paid. So for any observation, you can assume it just with no explanation. So that would mean that H of that proposition is true, but you have to pay its cost. So R of that proposition is also true, it's 1. I can go through this particular example in detail if there's interest, but to give you an overview, in this top row here, we're assuming unsafe is true, so H of U is 1, and R of everything else is 1 because we're not paying their cost, but we do have to pay the cost of assuming I-95 is unsafe, which is very expensive. And down at the very bottom, you can assume that snow has caused it all by assigning those integers. So what I have done in comma is turn analogy into a weighted abduction problem. The idea is that you have two sets of observations, a base and target, and each observation can be left unmatched or assumed at a high cost. I start off by computing match hypotheses in the same way that structure mapping engine does. And then from those root match hypotheses, I justify each expression as an observation by its alignment. So for each proposition in the base and the target, they can be explained if you align them to another proposition. Those expressions are in turn justified by other alignments. And I introduced candidate inferences as a way of explaining alignments for propositions that don't have a match. So that's kind of a quick overview of the approach. There's more details in the paper, of course. There's an interesting cognitive phenomena that young children seem to prefer matches of object and attribute similarity over matches of relational similarity. And there's competing theories around why this might be true. Some is that there might be a cognitive bias towards object and attribute similarity. Another is that richer relational schema might play a role. With comma, we can actually model this. And so I don't have much time to go into the details of the experiment that's in the paper, but the idea is that I can use comma to compare how my system will model analogies between objects that have shared relational versus same shared attribute similarity, and I can show human-like results. So these results are here. I'm happy to go through them in more detail. I just want to conclude by encouraging you to take a look at the paper. I formulate analogy as an ILP problem, and I've focused today mostly on the cognitive side of it, but I also think it's very useful for incorporating analogy into general abductive ILP solutions. So thank you very much, and I'll take questions.
I don't see anyone already priming us with a question.
Is there any in the chat? Yes, there are, so in the chat, yes, there are many other models of analogy. There's several great papers I can point you to that do comparisons between particularly SME and ACME and the rest of these. There are lots of different approaches. So yeah, if anybody has questions, happy to answer, or we can talk in the breakout rooms. So thank you very much for your attention.